Hey everybody, wind, it may seem like a gentle force, but over time, it is pretty powerful. Here's 15 amazing landscapes that were formed by the wind. Let's start with number 15, White Sands National Park. White Sands National Park, located in Tularosa Basin of southern New Mexico, is home to the world's largest gypsum dune field. It covers about 275 square miles, and its bright white landscape has been shaped almost entirely by the wind over thousands of years. Unlike most desert sand, which is made up of quartz, the dunes here consist of gypsum, a soft mineral that's highly soluble in water, making its presence in dune form exceedingly rare. The formation of these dunes began with the evaporation of an ancient lake known as Lake Otero during the last ice age, around 10,000 years ago. As the lake dried up, it left behind large gypsum deposits in the basin. Over time, weathering process, especially freeze-thaw cycles, broke down this gypsum into fine crystals. Seasonal rains carried the loose material into the lower areas of the basin, where shallow lakes formed and evaporated. Once these bodies of water disappeared, strong regional winds picked up the gypsum particles and began transporting them across the desert floor, creating these dunes in the process. Now, most of the dunes move at an average rate of about 30 feet a year, although some smaller ones can shift more quickly. This continuous motion means that the dunes are constantly being reshaped and re-exposed, creating an evolving landscape. There's 5 major types of dunes in the park: dome dunes, transverse dunes, barchan dunes, parabolic dunes, and sand sheets. Each one is formed depending on wind direction, strength, and the amount of available sand. Dome dunes, for instance, are low and circular and happen where wind is multi-directional. Transverse dunes, by contrast, form perpendicular to the prevailing wind and can grow very large in height and width. Despite the harsh appearance, though, the dune field does support a variety of specialized plant and animal life. Species like the white sands pupfish, bleached earless lizard, and several types of insects have adapted to this environment, and many of them exhibit pale or white coloration, which helps them blend in. White sands has been a subject of interest for decades. Geologists study the active dune dynamics, biologists monitor the unique species, and climate scientists observe how desert systems like this respond to environmental changes. The park is also used for missile testing in the adjacent areas, as it's surrounded by White Sands Missile Range, one of the largest military installations in the U.S. Public access, of course, is sometimes temporarily restricted. In 2019, the site was redesignated from a national monument into a national park, a change that helped elevate its profile and preserve it further. Number 14, the Pinnacles Desert in Australia. The Pinnacles Desert, located within Nambung National Park in Western Australia, is a coastal limestone landscape that features thousands of pillar-like rock formations that rise from golden yellow sand. These structures, known as pinnacles, vary in size and shape. Some of them are about 12 feet tall, while others are squat and irregularly shaped. Their distinctive forms have made the area one of Australia's most recognizable wind-sculpted landscapes. The origins of the pinnacles can be traced back tens of thousands of years to a period when the region was submerged. Seashells and marine life deposited large quantities of calcium-rich sand onto the coast. Over time, the deposits became compacted and formed limestone. The pinnacles began forming when sections of the limestone were exposed and chemically weathered. Rainwater, slightly acidic due to dissolved carbon dioxide, percolated through the sand and gradually dissolved parts of the limestone. Then over time, that process created voids and hardened zones in the rock. When the softer surrounding material was removed by wind, the more resistant vertical structures remained. One of the reasons these formations are so prominent is the ongoing activity of coastal wind. These winds constantly move sand around the pinnacles, revealing new structures while partially burying others. No two visits to the Pinnacles Desert are really exactly the same. Now, the surrounding desert is made up of primarily yellow quartz sand, which contrasts strongly with the pale limestone. The wind not only uncovers new pinnacles, but it also polishes and subtly reshapes the surfaces of the existing ones. The pinnacles aren't arranged uniformly across the desert, but they appear in clusters and scattered fields. Some researchers believe this may be due to variations in vegetation cover and water retention in ancient soils that influenced where limestone formation was strongest. However, not all the exact details of their distribution and formation are fully agreed upon, and some debate remains within geological circles. The site's been protected within the Namib National Park since the 1950s and is now a major tourist destination. A paved loop allows people to drive through the formations, and walking trails enable closer inspection. Interpretive signs and a visitor center provide background and ecological context, which emphasizes the importance of preserving these fragile landscapes. Number 13. The Great Sand Dunes National Park. Great Sand Dunes National Park is in southern Colorado. It's home to the tallest sand dunes in North America, with some reaching heights of over 750 feet. The dunes were formed entirely by the action of the wind over many thousands of years. This huge field of sand, covering about 30 square miles, is a prime example of how aeolian processes can create massive and complex landscapes. The origins of the sand begin with the erosion of the nearby mountains, which deposited sediments into the San Luis Valley through ancient rivers and streams. Over time, as the valley floor dried out and large bodies of water receded, the fine sand and silt left behind were picked up by the wind, blowing from the southwest. Once deposited, the sand didn't just stay put. Wind currents continued to move the material, shaping it into various types of dunes like the Barchan, transverse, and reversing dunes. The local wind pattern here is key to this. While southwesterly winds dominate during the day, northeasterly storm winds sometimes blow from the opposite direction. This bidirectional pattern allows dunes to grow vertically and change shape continuously, resulting in steep slip faces and complex ridges. An interesting factor in the formation of the Great Sand Dunes is the role of water. Two creeks, Medano and Sand Creek, border the dunes, and they help recycle the sand. After heavy rains or snowmelt, these streams transport sand away from the base of the dunes, and when they dry up, the wind picks up the sand again and returns it to the dune field. Now, the park is not just sand. It includes alpine lakes, forests, grasslands, and wetlands, creating a highly diverse ecosystem. More than 800 species of plants and animals have been recorded in the park. Despite the harshness of the dunes themselves, animals like kangaroo rats, darkling beetles, and short-horned lizards have adapted to life here. Plant life, though, is sparse on the dunes, but it grows in abundance on their margins. The dunes continue to move and evolve today. Monitoring by National Park Service has shown that the smaller dunes at the edge of the field can migrate several feet each year, and the tallest dunes, however, are relatively stable due to their massive size and the presence of stabilizing vegetation around their base. Number 12. The Sahara Desert Yardangs, Egypt and Libya. Yardangs are streamlined, wind-eroded ridges that are typically found in desert environments, and some of the most dramatic are located in the Sahara Desert, particularly in the western desert of Egypt across the Libyan desert. These landforms are carved directly out of the bedrock or compacted sediment by persistent wind abrasion and deflation. In the Sahara, yardangs can stretch for hundreds of meters and reach heights of 20 feet or more. Now, the word Yardang comes from a Turkic language spoken in Central Asia, but the term has been adopted globally by geologists. In the Sahara, yardangs are most commonly formed in areas where rock layers alternate in hardness, and the resistant layers erode more quickly when exposed to high-velocity winds, which carry sand and dust. The process is purely mechanical. Wind acts like a natural sandblaster, which gradually carves the narrowing rock into long, narrow ridges. Yardangs form in hyper-arid environments with very little vegetation or moisture, conditions that are ideal for sustained wind erosion. The western desert in Egypt is a prime location where these are exposed in abundance. The El Katara Depression, for example, contains thousands of these features, making it one of the densest Yardang fields on Earth. The geology of these areas often involves ancient lake beds or marine deposits that have been uplifted and exposed to erosion, and in many cases the yardangs form in consolidated clay, silts, or weak sandstone that have undergone limited lithification. Over time, the wind carves out hollows, sharpens the ridges, and eventually reduces the formations to low stumps or removes them entirely. Yardangs are not exclusive to the Earth either. Similar formations have been seen on Mars, where thin atmospheres and strong winds have sculpted the surface in comparable ways. The study of yardangs on Earth has therefore become useful in planetary geology, offering some clues about the process on other planets. Number 11. Barend Dunes. The Barend Dunes are crescent-shaped sand dunes formed in regions where the wind blows predominantly from one direction and there's a limited supply of sand. These formations are found in deserts around the world, including the Karakum Desert in Turkmenistan, the Taklamakan Desert in China, and parts of the Namib and Sahara deserts. Their distinct shape and movement patterns make them a well-documented example of a landscape shaped exclusively by the wind. A Barend Dune features a gently sloping windward side that faces the incoming wind and a steeper leeward side, known as the slip face, where the sand cascades downwards. The two horns or points of the crescent face downwind can extend far in the direction of sand movement, and these horns often move faster than the center, accentuating the curve shaped over time. A process known as saltation involves sand grains bouncing along the surface, and this helps the dune migrate slowly in the direction of the wind. Depending on wind strength and sand availability, the Barend Dunes can move several meters each year. The size of them can vary widely. Some are only a few meters high, while others may reach up to 30 meters in height and stretch more than 300 meters in length. In places in the Arabian Peninsula, Barends are often seen in large groups or dune fields, creating huge undulating patterns across the desert floor. Scientists study these dunes to better understand wind dynamics and sediment transport. In some regions, researchers use satellite imagery to track their movement over time. These dunes can also be indicators of changing environmental conditions, shifts in wind direction, sand availability, or vegetation cover. A really important factor in the formation and maintenance of these dunes is the scarcity of sand. When sand is abundant, dunes tend to merge and form broader transverse ridges. Barends, on the other hand, require relatively hard ground or bedrock beneath a thin sand cover, allowing the wind to sculpt the individual dunes. However, they can play a role in shaping desert ecosystems too by influencing airflow and providing temporary shelter for insects or small animals. Some deserts, like those in Mongolia or Peru, show evidence of past Barend Dune migration that affect archaeological sites or traditional settlements, which underscores their long-term impact. Number 10. Lençóis Marahenses, Brazil. The Lençóis Marahenses National Park in northeastern Brazil presents an unusual landscape, an expanse of bright white sand dunes stretching over 1,500 square kilometers interspersed with seasonal freshwater lagoons. While the pools of water form from seasonal rains, the creation and ongoing transformation of the dune field are entirely the result of the wind. This makes it one of the most fascinating examples of a wind-formed landscape on the planet. Situated along Brazil's Atlantic coast, this is unlike any typical desert in one critical way. It receives substantial amounts of rainfall, around 1,200 millimeters annually. However, the sand itself is deposited and shaped by coastal wind. The sand originates from river sediments, and once the sediments reach the ocean, wave action and ocean currents push them along the coast. During the dry season, prevailing trade winds from the east pick up the fine quartz grains and blow them inland, gradually forming a massive dune field. The dunes are mostly crescent-shaped, similar to Barends, but they're often irregular due to the influence of seasonal rain and underlying water table. They can reach up to 40 meters in height and stretch for several kilometers. Wind is the principal force responsible for their migration and the reshaping. And during the dry season, strong, consistent winds will blow the sand westward, gradually moving the dunes over time. From June to September during the rainy season, rainwater collects in the valleys between the dunes, creating thousands of temporary freshwater lagoons. Despite the transient nature of these pools, they support a variety of aquatic life, including fish that arrive through underground water channels or are carried as eggs by birds. These lagoons don't contribute to the dune formation, but they add a seasonal layer of ecological complexity. Though the presence of water here is visually striking, the landscape does fundamentally remain aeolian in nature. Even during the rainy season, wind continues to move the sand, albeit at a slower rate. This cycle of wet and dry has persisted for centuries, which allows the dune field to expand and evolve. The national park was established in 1981 to protect it, and it's part of the Caatinga biome. While parts of the park receive a steady stream of tourists, large sections also remain inaccessible and untouched. Unlike many dune systems that are defined by complete aridity, this one shows how wind can dominate the formation of landforms, even in environments with substantial precipitation. Number 9. The Valley of the Moon in the Atacama Desert of Chile. The Valley of the Moon is located in the Atacama Desert, and it's one of the driest places on the planet. This landscape, part of the larger Los Flamencos National Reserve near the town of San Pedro de Atacama, has been shaped extensively by the wind. Its terrain of salt, clay, and sandstone features steep ridges, sharp pinnacles, and natural amphitheaters, all carved by the wind over long timescales. The valley lies within a sedimentary basin where layers of sand and salt and gypsum were deposited over millions of years. As the region dried up and uplifted through the tectonic activity associated with the Andes Mountains, these layers were exposed to the atmosphere. With virtually no rainfall here, some weather stations have recorded no measurable precipitation for decades, water erosion plays no role here. Instead, wind is the primary force shaping the land. The winds transport sand and dust particles that abrade the exposed rock surface, and over time, the wind-polished surfaces take on strange forms, while weaker rock layers are worn away entirely. Some areas of the valley have become deeply incised by these winds, leaving behind sharp ridges and narrow ravines with walls that rise steeply from the floor. One of the most recognizable features in the valley is the so-called amphitheater, a large bowl-like depression with steep walls that was shaped by wind. Another well-known formation is the Three Marys, a trio of vertical stone structures that have been gradually sculpted by the wind into their current fragile appearance. The continual abrasion from airborne particles ensures that the landscape is slowly but steadily evolving. The wind not only sculpts, but it redistributes fine material across the basin, creating dunes and sand patches that move with the seasons. Temperatures in the valley fluctuate significantly between night and day, which does contribute to a secondary erosion process known as thermal stress. This causes rock to expand during the day and contract at night, making them more susceptible to fragmentation by the wind. However, this effect is minor compared to the long-term impact of constant wind-blown erosion. Because of its similarity to lunar and Martian terrain, NASA and other space agencies have used the Valley of the Moon as a terrestrial analog for testing rover components. Its features are sometimes compared to those of Mars, especially the yardangs and dust-sculpted rocks found in the Martian deserts. Though the area is remote, it's accessible to tourists, and designated viewpoints allow for some observation of the land without disturbing the fragile features. The Chilean government has enacted conservation measures too to protect the valley from overuse and off-road travel, which can damage the surface and accelerate the erosion. Number 8. The Big Daddy Dune. The Big Daddy, that's a great name for a dune. Big Daddy, it's one of the tallest sand dunes in the Namib Desert. It's located near the famous Sosuvlai salt and clay pan in the Namib Nakluft National Park in Namibia. It's estimated to rise over 325 meters, that's over 1,000 feet. Big Daddy is a striking example of a wind-formed landscape in one of the oldest and driest deserts in the world. Now, the Namib deserts existed in some form for roughly 55 to 80 million years, making it one of the most ancient desert environments on the planet. The sand in this region primarily originates from weathered rock carried by the Orange River, which empties into the Atlantic. Ocean currents then move the sediment northwards along the coast, where strong inland winds pick up the fine sand grains and carry them eastward into the interior. In the area surrounding Sossusvlei, the landscape is dominated by these massive star dunes, so-called because the ridges radiate in multiple directions. These form in environments where wind direction varies significantly. Big Daddy is one of the most prominent of these dunes. Its height and structure have been shaped by the interplay between the strong coastal wind from the west and occasional gusts from the east and north. Unlike some dunes that migrate quickly, Big Daddy is relatively stable due to its size and the wind convergence. However, its surface is constantly in flux. The slip face, the steep leeward side of the dune, regularly experiences minor collapses as sand builds up and cascades downwards. And surrounding Big Daddy is the clay pan, a white flat depression that occasionally fills with water during rare rain. These ephemeral lakes contribute little to the formation of the dunes, but they highlight the contrast between the dry, wind-shaped landscape and the brief episodes of moisture. Geologists study Big Daddy and its neighboring dunes to understand the wind behavior, the sediment transport, and the long-term desert evolution. The presence of distinct layering in the dune cross-sections also provides clues to past climate and wind patterns. Visitors can hike Big Daddy through a designated trail that runs along the ridgeline, and the climb provides expansive views of the surrounding dune sea. Strict rules prevent any off-path travel to preserve the fragile crust. Moving on to number 7, the Kelso Dunes. The Kelso Dunes, they're within the Mojave National Preserve in southeastern California, and they're one of the largest sand dune systems in the U.S. Covering an area of about 45 square kilometers or 17 square miles and reaching heights of over 650 feet, these dunes are entirely wind-formed. The origins of them that make up the Kelso Dunes is primarily attributed to erosion from the surrounding mountains, including the Providence and Granite Mountains. Over time, the sediment from these highlands was carried down by streams and flash floods into the ancient lake beds. When these lakes dried up, strong prevailing winds picked up the finer particles and carried them to the area where the dunes now reside. This wind-driven accumulation of sand likely began about 25,000 years ago during the late Pleistocene epoch. The primary wind direction in the Mojave is from the northwest, and this has influenced both the orientation and migration of the dunes. The result is a series of crescentic and linear dunes that continue to shift slowly with ongoing wind. Now, Kelso Dunes are best known for a unique phenomenon called booming or singing sand. When large amounts of dry sand move down the dune's slip face, the grains interact in a way that produces a low-frequency rumbling sound, sometimes audible for miles. While the exact mechanism is still being studied, it is believed to be related to the synchronized movement of sand grains and the internal structure of the dune. Not all dunes produce this sound, and those that do have to meet specific criteria. Unlike some dune systems that migrate rapidly, the Kelso Dunes have remained relatively stable. This is in part due to the enclosed nature of the basin and the limited supply of additional sand. Still though, their surfaces are constantly reshaped by the shifting wind, and new smaller dunes form on the periphery as sand continues to be redistributed. Because of their size and accessibility, the Kelso Dunes have been extensively studied. Research has included measuring wind velocity and sand transport, analyzing mineral composition, and documenting the dune's internal stratigraphy. The sand is mostly composed of quartz with small amounts of feldspar and magnetite, giving it a light color that reflects solar radiation. These dunes are protected as part of the Mojave National Preserve, and the National Park Service has implemented guidelines to prevent damage from any off-road vehicles. A designated hiking route allows people to ascend the tallest dune, which offers amazing views of the surrounding desert. Hikers are encouraged to stay on the marked paths to minimize any impact on these fragile crusts and vegetation. Number 6. The Dust Bowl Badlands. The Dust Bowl of the 1930s is one of the most well-documented examples of large-scale wind erosion caused by a combination of environmental conditions and human activity. The affected region, which included parts of Oklahoma, Texas, Kansas, Colorado, and New Mexico, experienced extensive landscape transformation due to severe wind-driven soil erosion. While not a natural dune system like others in this list, the Dust Bowl serves as a demonstration of how wind alone can alter the surface of the Earth, particularly when land is left vulnerable. Prior to the 20th century, the High Plains region was dominated by native prairie grass with deep root systems that held the soil in place. With the rise of mechanized agriculture and the plowing of millions of acres of land for wheat farming during the 20s and 30s, this protective vegetation was removed. When a prolonged drought struck the region during the early 1930s, the exposed topsoil dried out and became highly susceptible to the wind erosion. The Great Plains are known for strong and consistent winds, particularly from the west and northwest. During the peak of the Dust Bowl, these winds lifted huge quantities of topsoil into the air, creating enormous dust storms known as black blizzards. These storms could reduce visibility to a few feet, bury homes and machinery, and cause severe respiratory issues. Some dust clouds travel as far as the east coast of the United States, even reaching cities like New York and Washington. The scale of this erosion was unprecedented. In some areas, entire layers of topsoil, measuring several inches thick, were just stripped from the land and deposited miles away. While these weren't dunes in the traditional sense, the displaced earth sometimes accumulated into low mounds and ridges, which temporarily mimicked natural wind-formed landscapes. Recovery efforts included replanting native grasses, introducing contour plowing techniques, and establishing windbreaks, rows of trees or shrubs planted to reduce the wind velocity. However, some areas never really fully recovered, and scars from the era can still be seen in parts of the Oklahoma and Texas panhandles, where the land remains less fertile or visibly altered. Though caused by human mismanagement, the Dust Bowl does show the immense power of wind as a geomorphic agent. Unlike the slow and steady formation of natural dune systems, the Dust Bowl changes happened rapidly within just a few years, showing that wind erosion can be both sudden and severe under the right conditions. It shows that while wind can sculpt beautiful and gradual features in natural deserts, it can also quickly devastate the landscape when natural buffers are removed. Number 4. Simpson Desert Longitudinal Dunes. The Simpson Desert in central Australia is home to one of the largest and most uniform networks of longitudinal dunes on the planet. They stretch for over 176,000 square kilometers, and the desert features more than 1,100 parallel sand dunes, some of which run unbroken for more than 200 kilometers. These long linear dunes are formed almost entirely by persistent bidirectional wind. Longitudinal dunes, also known as seef dunes, from the Arabic word for sword, form when the wind blows from two similar but slightly offset directions. In the Simpson Desert, these winds primarily blow from the southeast during the summer and the northeast during winter. As sand is moved by both wind directions, it accumulates along an axis that lies between them, resulting in long, narrow ridges of sand. The dunes vary in height, but they can reach up to 40 meters or about 130 feet, with inter-dune corridors typically about 1 to 2 kilometers wide. The sand that forms these dunes is believed to have originated from the erosion of rock formations in nearby regions, such as the Lake Eyre Basin, and deposited into ancient lake beds, where they were later picked up and redistributed by the wind. Unlike transverse or crescentic dunes, which often shift quickly, longitudinal dunes are more stable and enduring. Their shape allows wind to flow over them rather than disrupting them, and the regular spacing and parallel alignment of the dunes are so consistent they're easily visible in satellite imagery. Vegetation here is sparse. It's present in parts of the Simpson Desert, particularly in the swales between the dunes. Hardy plants like spinifex grass, acacias, and saltbush help trap wind-blown sand and stabilize the landscape. The desert here receives very low rainfall, averaging less than 150 millimeters per year. The conditions ensure that wind remains the dominant force, with little interference from any water-driven process. While remote, the desert is accessible through a few marked tracks and has become a destination for researchers and adventurers. Regulations limit vehicle access in certain areas to prevent damage to the fragile dunes. Number 3. The Namib Sand Sea, Namibia. The Namib Sand Sea is located across the southwestern coast of Africa in Namibia, and it's one of the most expansive and studied landscapes in the world. It was designated a UNESCO World Heritage Site in 2013, and it covers more than 30,000 square kilometers and includes thousands of dunes shaped entirely by the wind. The Sand Sea is part of the Greater Namib Desert. That's one of the oldest deserts on the planet. Some dunes here have likely existed in various forms for millions of years. The proximity to the Atlantic Ocean is a critical factor in the formation of them. The cold ocean currents along the coast cause moisture-rich air to condense into fog, which drifts inland and provides the only regular source of moisture in this otherwise hyper-arid region. The sand itself is largely from sediments carried by the Orange River, which flows from the highlands of South Africa and deposits material into the Atlantic. From there, the strong persistent onshore winds blow the dry, fine sand inland, forming these vast dune fields that stretch hundreds of kilometers. The central region here features star dunes, which grow vertically and have multiple arms formed by multi-directional winds. These dunes can exceed 300 meters in height and are relatively stable over long periods. In other regions, Barchan and transverse dunes dominate, though, created by more consistent unidirectional winds. Despite the climate, though, that fog drifting in from the ocean can penetrate up to 100 kilometers inland. This fog plays a critical role, and it influences the formation and stability of the dune surface. While fog isn't responsible for forming them, it does influence the rate at which they can shift. The wind here is dominated by southwesterly trade winds. Now, these winds are strong and dry, capable of transporting sand from across huge distances. Ecologically, the Namib Sand Sea supports a surprisingly diverse range of organisms that have adapted to the harsh wind-shaped environment. These include fog beetles, which harvest the moisture from air droplets on their bodies, geckos with transparent skin to reflect sunlight, and sidewinder snakes that use specialized locomotion to move across soft sand. Of course, the area has drawn the attention of geomorphologists, climatologists, and ecologists alike. Science studies of the Namib Sand Sea have contributed to our understanding of sediment transport. The desert's also used as a model for interpreting aeolian features on other planets, especially Mars. Number 2. The Ebro Delta Dunes. The Ebro Delta is located in the autonomous region of Catalonia in northeastern Spain, and it's one of the most important wetland areas in the western Mediterranean. It also contains an often overlooked but significant series of coastal dunes. These wind-sculpted dunes are shaped by the interaction between fluvial sediment delivery, tidal action, and persistent coastal wind. The Ebro River carries sediment eroded from the Pyrenees Mountains and deposits it into the Mediterranean, forming a large delta that's been expanding seaward for thousands of years. The fine-grained sands deposited at the river's mouth are easily picked up by prevailing wind, particularly from those in the northwest, known locally as the Mistral and Tramontana winds. These winds have played a major role in reshaping the coastal edges of the delta. The most prominent formations here are the transverse dunes, which develop perpendicular to the direction of the wind. These dunes are often low in height, ranging from a few meters up to around 10, but they can stretch for kilometers along the coast. Vegetation does play a stabilizing role in the dune system. Native plant species like European beach grass help anchor the dunes by trapping wind-blown sand with their stems and root networks. The dune systems here are closely monitored due to their sensitivity to both natural and anthropogenic change. Rising sea levels, changes in sediment flow due to upstream dams, and coastal development have all impacted the delta's ability to maintain its equilibrium. Where sand supply is reduced, wind continues to move the existing dunes. Despite their modest size compared to those in major desert systems, the Ebro Delta's dunes serve as an important case study in coastal process. They demonstrate how wind can continue to shape the land even in regions with significant moisture, vegetation, and human presence. Monitoring stations will track sand movement and vegetation health and should help scientists assess the long-term viability of the dunes under these changing climatic and environmental conditions. Number 1. The Empty Quarter, Rub al Khali. The Rub al Khali, or Empty Quarter, is one of the most expansive, continuous sand deserts in the world, covering parts of Saudi Arabia, Oman, the United Arab Emirates, and Yemen. It spans more than 650,000 square kilometers, and it's characterized by an enormous array of wind-formed dunes. The sand in the Empty Quarter is primarily derived from the erosion of ancient sandstone and limestone formations that date back to the Tertiary period. Over millions of years, weathering broke down the rocks, and the resulting sediments were transported by rivers and deposited in large basins. The Rub al Khali contains a variety of dune types, including linear, barchan, star dunes, and complex compound dunes. Some of the tallest ones rise over 250 meters. Star dunes, massive pyramidal structures formed by multidirectional winds, are really prominent in the central and southern portions of the desert. One of the defining features of the Empty Quarter is its isolation and lack of water. This extreme dryness limits vegetation almost entirely. The absence of stabilizing plant life means smaller dunes and sand sheets can migrate relatively quickly. The composition of the sand also contributes to its movement. Rich in quartz and feldspar, the grains are well sorted and rounded, making them easily mobilized by even moderate winds. Despite the conditions, though, the Rub al Khali has been a focus of scientific interest for decades. Satellite imagery has revealed ancient riverbeds and lake basins beneath the sand. While these buried features are now inactive, they still influence the substructure of the desert and may help explain certain patterns in dune distribution. While nearly uninhabited today, the Rub al Khali has historical significance as a barrier and transit zone for ancient trade routes. Archaeological finds at the edges of the desert suggest intermittent human presence, often centered around ephemeral water sources. However, the core of the desert remains one of the most uninhabited and wind-dominated places on the planet.